first lecture of a mini course on effective circle count for Apollonian circle packings. The first lecture will be via spectral methods.
Okay, thank you. Since I'm one of the organizers, so I'd like to thank participants to give me this chance to speak here. So yeah, as the title says, I'll talk about circle counting result for Apollonian circle packings. And since I'm almost sure like everybody knows what Apollonian circle packings are, but I'd like to still explain, actually, define what they are first. So the construction of Apollonian circle packing actually goes back to this ancient theorem of Apollonius, which is about 200 BC. So the theorem says given 3 mutually tangent circles in the plane, there are precisely 2 circles. 2 circles which are tangent to all the 3 circles. 2 circles tangent to all 3. Okay, so you can imagine, like, suppose we have these 3 mutually tangent circles, and then the claim is there are precisely 2 circles which are tangent to all of them, and then so obvious choice would be these 2 circles. Okay. So we'll prove actually this Apollonian theorem, and this might be probably the only proof I'm giving actually in this course, but the proof will be actually the modern proof based on Möbius transformations. And I'd like to talk about these Möbius transformations anyway, because it will come actually later as well. So the proof uses Möbius transformation. And by Möbius transformation, we simply mean this linear fractional transformation, A, B, C, D. Z goes to, so here A, B, C, D are complex matrices. And AD minus BC, the determinant has to be 1. And then AZ plus B over CZ plus D. So this is Möbius transformation, and then its well-known property is that this maps circles to circles. And then in this talk, when I say circle, it always includes lines. So lines in the plane are also circle. And preserving angles between them. So in particular, if you have 2 tangent circles, then Möbius transformation will map 2 tangent circles to 2 tangent circles, because it will preserve the angles. So now actually, so how do I now prove that we can really actually draw the 2 circles which are tangent towards 3? So you take arbitrary point, one of the tangent point here. Let's call this tangent point P, and choose a Möbius transformation which maps P to infinity. Okay? Then these 2 circles which are tangent at P should be mapped to 2 circles tangent at infinity. So A will be, say, Möbius transformation, which maps P to infinity, and then these 2 circles will be mapped to 2 circles tangent at infinity, so namely these 2 parallel lines. And since this third circle should be tangent to these 2 circles, there is only one choice. It has to be mapped to this circle. And now in this configuration of like 3 mutual tangent circles, it's clear that this Apollonius theorem actually holds. So we can draw these 2 circles here. And these are precisely 2 circles the Apollonius theorem claims. And then we can go back to the original configuration using A inverse, and then we prove that, in fact, actually these 2 circles exist. So this is the theorem of Apollonius. So this theorem is the basis of the construction of what's called Apollonian circle packing. And so to construct Apollonian circle packing, we start with 4 mutually tangent circles. Okay? So begin with 4 mutually tangent circles in the plane. And so here are possible configurations of 4 mutually tangent circles. So we've already seen that you can have this one, or you can have this one, or you can have also this one also, or you can also have this one. Okay. So begin with any of these 4 mutually tangent circles. We'll add, so by Apollonius theorem, you can add circles tangent to 3 of the given ones. So we have 3 mutual tangent circles, and then here is a 1 circle. So by Apollonian theorem, there has to be another circle which is tangent to 3 of them. And then we keep actually repeating the same step of adding circles which are tangent to 3 of the previous circles. And then we obtain infinite circle packing called Apollonian circle packing. Okay. So here is some possible, yeah, I've drawn, I think, I don't know, 5 or 6 generations of Apollonian packing. So we start with maybe these 4 mutually tangent circles, and then you keep adding newer circles. But in this picture, we are adding exactly 1 circle in each triangle interstices, and then we obtain this infinite circle packing. And if you had started with 4 mutually tangent circles containing these 2 parallel lines, then we would have arrived actually this infinite circle packing. But there are also other unbounded Apollonian circle packings which contains just 1 line or which does not contain any line. Okay? But these Apollonian circle packings it's hard to draw because the circles will get enormously large only after a few generations. So, okay? So these 2 pictures actually, the example of Apollonian circle packings actually I want to state the theorem. So the counting circle problem is this. So we now fix Apollonian circle packing. And when P is bounded, the following counting function is well defined. So we define n sub Tp to be, say, number of circles in P of curvature of circle less than T. Okay? So since P is bounded, so there cannot be actually, so what is curvature? So the curvature is 1 of the radius of the circle. So since P is assumed to be bounded, there can be only finitely many circles of curvature less than T. So this will be finite number for every T. And we can also define a counting function for Apollonian packings of this type. Even though this is unbounded packing, so there are infinitely many circles of the same actually curvature. So that function will not be defined well, but then if you just restrict our counting function to 1 fixed period, then it will capture, the whole Apollonian packing, but also the counting function can be defined. So if P, say P is this one, so I'll just use this notation. Okay. Then this n sub Tp is the same thing, but just in a fixed period. Then the counting function can be well defined. Okay. So the counting question is, what is the asymptotic of this n sub Tp as t tends to infinity? And this counting function actually turns out to be related to the metric structure of actually the underlying fractal set coming from this P, and that is called the residual set. So let me define what is called the residual set of P. So residual set of P will be simply, we can define to be, you look at all the circles contained in P, and then take the closure in the plane. Okay? So here we have lots of countably many circles, but we take a closure of the union of circles in the plane, and that's the residual set. So this is same as we simply actually remove from the complex plane union of all the interior of the circles from P. Okay? So it's the same definition. And another important invariant which appears in this counting function is the residual dimension, so which I'll denote by alpha. So alpha will be the residual dimension. The interior, right? I didn't talk about the orientation of the circles, right? So I orient the circles so that they have disjoint interiors. So this outer circle actually has interior, which is the exterior of the circle. Yeah, then maybe I can remove this definition and just use this. So alpha is the residual dimension of P, which is simply mean the Hausdorff dimension of the residual set of P. Okay. So first note that actually this alpha is independent of the choice of P. Because actually in the proof of Apollonian theorem, actually, we saw that actually, if you have any two Apollonian packings, and then if you choose Möbius transformation, which moves the three tangent points to three tangent points of the other Apollonian packing, then we get actually equivalence of these two Apollonian packing, and then the Hausdorff dimension actually does not change under Möbius transformation. So you get this residual dimension, which is independent of P. So how big is this? So exact number is not known, but it has been approximately known to be this number, and I think this is due to Kurt. So you see actually this, the fractal state is quite big. I mean, we have this countable union of circles, but then when you take the closure, actually the Hausdorff dimension is much bigger than 1. So it's quite big. So first the result about this actually counting question goes back to Boyd. So he computed the limit of log of n sub tp divided by log of t as t tends to infinity. So this converges to the residual dimension of P. Okay. And this does not quite say, but this does not quite say what is the asymptotic of this. And so it was a question actually whether, for instance, n sub Tp is constant times t to the alpha times if there exists extra log term or not. Okay. So it was not clear whether there is extra log term or not. And some, I guess, some poor numerical actually experiment made it believe that actually there might be some extra log term. Okay. And so theorem. So the first theorem is with Kontorovich, Alex. We show that there is no log term. So first, n sub Tp is asymptotic to constant times t to the alpha. So this goes back, I think, about 2009, and around maybe 2010 or 11 with Nimisha. We proved this result, but a different approach, and that actually made this constant much clearer, actually, this approach. And this result says that this here main term, the contribution of main term actually can be stated this way. So there is some constant, Ca, and then H alpha of residual set of P times T to the alpha. And so where, so this H sub alpha of residual set of P denotes alpha dimensional Hausdorff measure of residual set of P. And this C sub A, this constant which I propose to call Apollonian constant, is independent of P. So again, I should say that the residual, when I said the alpha dimensional Hausdorff measure of residual set of P, so when you look at actually this type of Apollonian packing, again, the Hausdorff dimension, we only measure actually the residual set in a fixed period. Okay. It's not obvious result, but actually for Apollonian packing, this alpha dimensional Hausdorff measure is actually a locally finite positive measure. So actually, this constant is indeed positive. And the reason, I mean, that I proposed to call this constant Apollonian constant is that actually, so this is independent of any packing P. In particular, you can think of C of A to be the limit of n sub Tp divided by this Hausdorff measure times T to the alpha. For any bounded Apollonian packing, you can choose your simplest bounded Apollonian packing, and then the Apollonian constant is given like this. And I don't know actually any estimate of this. So we have some formula of C of A, which is actually some fraction of some highly singular measure coming from the hyperbolic three-dimensional hyperbolic manifolds, but don't know explicit number. And it will be interesting, I think, to have at least some estimate of this constant C sub A. So modulo this C sub A, I mean, we have actually pretty good understanding of this counting function. And now very recently, the Minni, so we obtained the error term in this counting result. So now can say n sub dp, c sub a, h alpha residual set of p. Let's say t. What is this sum? Oh, it's maybe not in that case. T sub alpha and 1 plus O T sub minus eta. Okay. Again, where eta is a constant independent of P. So this is the effective circle count result actually I want to discuss today, the third result. But actually before going to the proof of this statement, I want to say that actually this approach with Nimisha actually proves something stronger, which is about the distribution property of circles in Apollonian packing. In fact, it shows that this alpha dimensional Hausdorff measure in the residual set of P actually describes the asymptotic distribution of small circles in any Apollonian packing. So to state that, so let P be either bounded or unbounded. So here we don't have to restrict ourselves to two unbounded packing between two parallel lines, but it can be any unbounded Apollonian packing. But the counting function will be well defined if you define n sub Tp comma E. So here let E be any bounded region in the plane. So E is any bounded set. So instead of counting all the circles, if you count the circles in P of curvature less than T, but this time we'll be counting circles which intersect this bounded region. Okay? So you take some bounded region E, and then just count the circles which intersect this region E and then of curvature less than T. Then because E is bounded, so this is well defined for any Apollonian packing. And theorem says that now. So we assume E is any bounded region, but with a smooth boundary. Suppose the boundary of E is smooth. Then this n sub T P comma E is asymptotic to, again, the Apollonian constant times the intersection of the residual set of P and E. So it's the alpha dimensional Hausdorff measure of residual set of P intersection E times T to the alpha. So in particular, of course, as an easy consequence of this result is that for any E1, E2, again, bounded regions with smooth boundaries, if you look at the ratio of two counting functions restricted to E1 and E2, then its ratio is asymptotic to exactly the ratio of the Hausdorff measures of E1 and E2. Eventually, actually, so we expected, in fact, actually, so this, we should be able to compute actually error term in this result as well. Okay, so now actually, so I want to actually so focus on this result and then explain where this error term comes from, and then what is the corresponding result actually in ergodic theory of, say, infinite volume hyperbolic manifolds actually, which is responsible for this error term. So I'll go over some basic concept in hyperbolic three-dimensional hyperbolic space. So I'm going to use upper half space model. So we'll see actually very soon actually this upper half space model for hyperbolic space actually is the most natural model actually for this problem. So H3, so x1, x2, y. So y is just positive. So here we have so we have this upper half space over this x1, x2 plane. So this is H3, and then the metric is simply the Euclidean metric divided by the third coordinate here, y. Okay. So in this model, it's clear that the boundary of this pop space can be identified with this x1, x2 plane, which I again identified a complex plane and point at infinity. So boundary of H3 is C hat or C union infinity. Okay. So now the group of Möbius transformation actually that we defined in proving Apollonian theorem can be identified with the isometry group of this pop space. So the PSL2C. Actually, like throughout my talk, it's a big abuse of actual notation, but I identify PSL2C with a group of Möbius transformations. It's not correct because the Möbius transformation has an inversion, which gives the determinant -1, but it's only like finite index problem, so I'll just say that PSL2C is a group of Möbius transformations, even though it's not correct. So we can identify this PSL2C. So PSL2C acts on this boundary with infinity by Möbius transformation, and this action actually can be lifted to the isometry of H3. But this honest PSL2C corresponds to orientation preserving isometries. And this identification is called the Poincare extension. So to explain this Poincare extension, so the group of Möbius transformations is generated by inversions with respect to circles. Okay, so I just have to explain what an inversion with respect to circle gives you isometry in H3. Okay? Suppose I have an inversion here with respect to some circle. Then we look at the northern hemisphere above this circle. Okay? Then this inversion with respect to this circle actually will correspond to inversion with respect to this northern hemisphere. And it's clear that this inversion will actually preserve the pop space. Okay? And you can also show that it preserves the metric. So it gives the isometry of H3. Okay? So this is the Poincare extension. And so now for the group, so this will be our G. And suppose gamma is a discrete group of G. So these groups are called Cranial Groups. And we'll always assume that gamma is not non-elementary, or in this case, it's the same as non-virtually abelian. So it's not virtually abelian. And two basic definitions actually about this discrete group of PSL2C is the limit set. So the limit set of gamma can be defined in many different ways, but in this case we can simply define this way. So you take any point in the boundary, and then you look at the orbit of gamma of Z. Okay, so you get some points over here, and then we collect the set of accumulation points. So that is the limit set of gamma. So you can say here the set of all accumulation points of gamma of Z for any Z. Okay, so you can use any Z, but it will give you all the same definition. And then second important invariant of this group is what's called the critical exponent. And this is simply the abscissa of convergence for the Poincare series defined by e to the minus s distance O gamma O, gamma from gamma, and then O is any fixed point inside H3. Virtually abelian means up to finite index is abelian. So it has a sub-row finite index which is abelian, and then not virtually means it's the opposite of that. Yeah. So the virtually abelian case actually will correspond to the case that the limit set has actually at most 2 points. So you want to eliminate the case. So among discrete groups actually so important class of discrete groups are so-called geometrically finite groups. So as the name indicates actually, so this has some good, these are discrete groups which has some good finiteness properties. So the definition of geometrically finite Again, it has several equivalent definitions, but I'll give you the simplest one. So in this case, you can say that gamma has a finite-sided fundamental domain inside H3. Okay? So this has finite-sided fundamental domain. So, I mean, you can also define the same notions for groups of PSL2R, and then in that case, the geometrical finite is equivalent to gamma is finite generated. But then in PSL2C, most of the time finite generated is not enough, but you need actually stronger property of this geometrical finiteness. For groups which are geometrically finite, this critical exponent turns out to be same as the Hausdorff dimension of the limit set. So this is same as Hausdorff dimension of the limit set. And moreover, it has a full critical exponent if and only if gamma is a lattice. Or this corresponding hyperbolic manifold has finite volume. So I assume actually also the gamma is torsion free. Okay. It's not very important assumption, but then to have this quotient as a manifold. Okay. Okay, so now using this preliminary stuff, so now I can explain how this Apollonian circle counting problem is related to cone counting problem. Okay. So it turns out that actually, so counting circle problem, we can translate this counting circle problem to a counting an orbital problem in a cone given by some quadratic form of signature 3,1, and that actually passage is given by this old theorem of Descartes. Okay, so I think it's about this. Okay. So the theorem says that you start with any quadruple of 4 real numbers. Let A, B, C, D be any quadruple of 4 real numbers, and this quadruple is what is called the Descartes quadruple. So Descartes quadruple is the terminology for quadruple of, it's the curvatures of 4 mutually tangent circles. So curvatures of 4 mutually tangent circles. So for given quadruple 4 real numbers, it can be realized as a curvature of 4 mutually tangent circles in the plane if and only if it satisfies the following quadratic equation, which I'm going to call Q. So A, B, C, D. So twice over minus A plus B plus C plus D squared is equal to 0. Okay. So this is amazing theorem. I mean, once you realize, I guess the proof is not very hard, but then, I mean, observation was very crucial. So to know that, I mean, given quadruple 4 real numbers, actually, if you can draw 4 mutual tangent circles, like you only have to check this condition, and then, in fact, it shows that actually you have plenty of configurations of 4 mutually tangent circles, because for any solution of this quadratic equation, you can draw this configuration of 4 mutually tangent circles. Okay. So it may not be clear, but then this quadratic form has a signature 3,1. So by this Descartes theorem, so P be any Apollonian packing, so Apollonian circle packing. So we have this bunch of circles like this. And you look at all the Descartes quadruples associated to this P. So consider all Descartes quadruples associated to P, meaning that we consider all possible 4 mutually tangent circles arising from P and then look at their curvatures. So we get a bunch of like vectors in R4. And by Descartes theorem, that gives us points in the cone. So we have here quadratic form, this Descartes quadratic form, Q is equal to 0. And then all Descartes quadruples associated to P will give us a bunch of points over here, right? Because for every Descartes quadruple, we get 1 point in a cone. Okay? And of course, it's not clear actually whether these points will be discrete set of points or you might have some accumulation points over here. But it turns out that this, the set of all Descartes quadruple associated to P is in fact one single orbit of a group called Apollonian group. So what is the Apollonian group? So we pick 4 mutually tangent circles associated to P, and then we look at the dual circles. So by dual circle, I mean, here we have 6 tangent points. And the 3 tangent points determine one circle. This. Okay. So we get 4 actual mutual tangent circles which are dual to actually given these 4 mutual tangent circles in P, and we'll denote by A the group generated by invergence with respect to these dual circles. So first, it's easy to observe that actually this group preserves the Apollonian packing. So for instance, maybe let's look at inversion with respect to this dual circle. Then it meets actually, so let's see. It meets 3 circles actually. Well, somehow don't see this right away. I have this one. What does it invert to? Maybe. It inverts 3, it fixes 3 circles which it meets perpendicularly, maybe because my picture doesn't give me perpendicular circles, that's why I don't see. So it fixes 3 circles that it meets perpendicularly, and then it maps exactly one circle which is tangent to those 3 circles to the other circle which is tangent to these 3 circles. So it preserves this Apollonian packing. So it is a symmetry group of the Apollonian packing. So, yeah, we'll figure this out later. So this depends on P as it is, because we started with this explicit configuration and then defined this A sub P. Okay? But since all Apollonian packings are actually equivalent to each other by Möbius transformations, these groups are all conjugate to each other as well. So this all Descartes quadruples associated to P actually, so this turns out to be one orbit of this group of, say, C1, C2, C3, C4. So we fix 4 mutually tangent circles, and then you look at all the possible, actually, 4 circles which arise from orbit of this Apollonian group. Then we get all the 4 mutually tangent circles coming from this P. So this AP is a subgroup of PSL2C. Again, I'm lying here. It has inversion, so it has a determinant -1, but okay, it's a subgroup of PSL2C up to plus minus 1s. And moreover, it turns out that actually we can find a representation of PSL2C going to SOQ of R. Okay. So I have here quadratic form. So if you look at the orthogonal group corresponding this quadratic form, this orthogonal group preserves the level set. So therefore, it preserves the cone, right? And then it has a signature 3,1, and then signature 3,1 orthogonal group is all isomorphic to PSL2C, but we can actually find the explicit actual representation here, which maps actually, so the corresponding picture will now be actually the orbit of Apollonian group over a fixed point here. So I have C1, C2, C3, C4, so that this will give me a 1 point in this cone, so let's call that V0. And then here I have Apollonian group. So now if I look at the orbit of this V, under this Apollonian group via this representation, in fact, we get actually all Descartes quadruples associated to P. So this is actually transition going from circle counting to this counting. Oh, I forgot, right. Right, so about this effective statement, effective circle counting statement. So I received a paper last night from Vinogradov, who is a student of Sinai and Kontorovich, and he claims that he also proves the effective statement like this. Okay? But his proof is different, and then I believe actually the error term we get is better than his error term. But I didn't have time to look at the paper, but I believe there is another way to do this. Okay. Now what? Right, so because of this, so moreover, so now this n sub Tp can be translated precisely. So here I have this orbit, and then so now I have this Apollonian group acting on this cone. So you start with one fixed vector v naught associated to this p, and then we have this orbit of this Apollonian group here. And then you count all the vectors in this orbit of Apollonian group such that the maximum norm of this vector is less than t. And then times actually there is something stabilized of this v naught in gamma plus 3. Okay. So more one can prove this, and then actually this relation shows that also this v naught a is discrete. So you don't always get discrete orbit, but it's discrete exactly when this counting function is well defined. Okay. So if it's not discrete, that means there is some accumulation points, which means that if you believe this relation, then we have some infinitely many circles of bounded curvature. Okay. So this discreteness precisely corresponds to n sub Tp bounded, or in other words, it corresponds to exactly either p is bounded or p is between these two parallel lines. Okay. So in some sense, actually, this the counting method via cone works precisely for these two types of Apollonian packing because of this relation here. Okay. So now, and moreover, I should also say that this group A is geometrically finite. Because A is generated by inversions with respect to 4 circles here. So if you look at the action of A in H3, so this is generated by inversions with respect to these 4 northern hemispheres above these dual circles. And the fundamental domain for groups generated by inversions which are either disjoint or tangent to each other is simply the exterior of these northern hemispheres. So we have only finitely many sides actually for this fundamental domain. So you get geometrically finite group. And moreover, the limit set of this Apollonian group turns out to be precisely the same as the residual set of P. Okay. In particular, the critical exponent of this Apollonian group is same as alpha, which is bigger than 1. Okay. So now, based on this observation, so this circle counting problem follows from this counting problem for cones. So suppose I have a representation, say PSL2C, going to SOQR. So here Q can be any quadratic form of signature 3, 1. So any real quadratic form. Of signature 3, 1. And take a vector which lies in the cone. So V naught is some non-zero vector lies on this cone. And let gamma be a discrete sub of PSL2C, which is geometrically finite, with delta strictly bigger than 1. And then we also assume that the orbit of gamma, orbit of V naught under gamma is discrete. Okay. Then now, for any norm, on R4, we can count number of vectors in this orbit, V naught gamma, of norm less than, say, t. Then this is asymptotic to constant times t to the delta, where delta is the critical exponent of gamma times 1 plus big O of t to the minus eta. So this circle counting for Apollonian packing is a special case of the theorem via that interpretation. And maybe I say that if the norm is Euclidean norm or K-invariant norm, actually, this theorem was proved in my paper with Kontorovich. But the problem was that in Apollonian packing, so problem, we have to look at the maximum norm, which is not like K-invariant norm. So that was why we couldn't get the effective statement for the counting circles in Apollonian packing. And then since actually this statement, this theorem works for any norm, in particular, use the maximum norm, and then we get this error term. So therefore, actually, this gives the error term in Apollonian packing. And what is eta here? So where eta depends only on the spectral gap. Okay, for gamma. Okay, so now I will explain what the spectral gap is. Maybe tomorrow Alex Kontorovich will explain this terminology, but let me do it here. So here actually to define this spectral gap, so we use this result. I mean, we use this assumption delta is bigger than 1. So when delta is bigger than 1, Lax Phillips actually proved that. So here I use delta bigger than 1, also gamma geometry finite. In this case, if you look at the Laplace spectrum on L2 over H3 over gamma, then there are only finitely many eigenvalues of Laplace operator. Actually, we want eigenvalues to be positive, so actually it's a negative of the usual hyperbolic Laplacian. So above or below the continuous spectrum 1, infinity of the type. So the smallest is always given by delta times 2 minus delta, and this eigenvalue is always simple. And then we get alpha 1, so let's call this alpha 0, and then alpha 2, and then alpha m. Okay. So this spectrum consists of the following form. So we always have this continuous spectrum from 1 to infinity, and then you have only finitely many actually discrete spectrum below 1. And then the smallest one is given by precisely this quantity here, delta times 2 minus delta. And of course, if delta is equal to 2, this will be 0, right? So, but if delta is not 2, then this is positive number. And then the spectral gap is called exactly, refer to the difference of actually these two smallest eigenvalue. So this difference here, alpha 1 minus alpha 0, is called the spectral gap of gamma. Oops, I'm running out of my time. Yeah. Since I'm running out of my time, so actually maybe I was going to state the next theorem, but I'll just say what it is. So because actually this eta depends only on spectral gap of gamma, so if you have a family of finite index subgroups of gamma, then in fact actually you can state this counting statement uniformly for all family of these finite index subgroups. And this family of finite index subgroups exists, for instance, in the arithmetic situation. So if you assume gamma to be contained in SOQ of the integral points, and then for D square-free integers, if you look at finite index subgroups of gamma, which contains these principal congruent subgroups of mod D, then this Bourgain-Gamble-Sana proved that actually they have a uniform spectral gap. So uniform spectral gap means that here there is a uniform epsilon such that this difference is bigger than epsilon for all of this family. Okay? So when you have this uniform spectral gap, you can actually change this gamma to be the family's gamma sub D, and then from the explicit description of constant, the only change will be C divided by index of this gamma sub I or gamma sub D inside gamma. And then the eta will be uniform for all these congruent subgroups. And this is important input when you want to use affine linear sieve to study primes or almost primes in the orbit. Okay? So this having this type of effective statement for this counting theorem is pretty important in the application to affine linear sieve because of this transition actually because of this condition that once you can get actually this error term depending only on the spectral gap, then now this great theorem of Bourgain-Gamble-Sana can be applied actually to use these affine linear sieves. Okay, so now where is horosphere? So now I explain how the equidistribution of horospheres intervenes actually to prove the theorem like this. So So this horosphere comes from the cone. So we have this cone defined by Q is equal to 0. And so I have this action of PSL2C on this cone. And then this action of PSL2C is transitive except for the origin. So this space, Q minus 0 minus the origin, can be identified with a quotient space of PSL2C. And then the stabilizer is isomorphic to this group NM, where N is simply the upper triangular group. And M is this just circle group. And these groups, since actually, so we are looking at the discrete gamma orbit on this quotient, it's kind of standard in this ergodic theoretic approach that, so the important ingredient will be understand the translation of n orbits. So understand the translation of, so let me write it like this. Gamma, gamma, and G modulo gamma. Okay, I'll try to explain how does this cell look like. Okay. So when you're talking about this hyperbolic 3 space H3, so we looked at this half space model. And if you fix this point, J, say 0, 0, 1, then this extension of PSL2C as action on H3, actually, you can compute that the stabilizer of this J corresponds to the spatial unitary group. So that means you can identify H3 with G PSL2C modulo K. Okay, K is PSU2. So this gives an identification of hyperbolic space with the G over K. But the unit tangent bundle, so now if I look at this vector, this is upward normal vector of length 1. Then again, PSL2C actually acts transitively on all the vectors in the unit tangent bundle. And then the stabilizer of this vector will be exactly this rotation. So it rotates like this. So it does not actually move this vector. So the unit tangent bundle, T1 of H3, can be identified over G over M. Okay. So this shows that if you look at the unit tangent bundle of the hyperbolic manifold, T1 H3 gamma, you can in fact identify this as a double quotient over G over gamma of M. Now, what is the N orbit? So here, N is just 1Z01. So this is simply translation when you look at the Möbius transformation action. And if you look at the orbit of N of this vector, then it gives you actually this horizontal plane, all the actually upward normal vectors. So this upward normal vectors gives you precisely this E and so it's an orbit of identity in E in this unit, in this actually identification of the quotient space. So, and what is A sub y? So I guess I didn't say what is A sub y. So A sub y is the diagonal matrix which corresponds to the geodesic flow. But here, so A sub y is the square root of y, square root of y inverse. Okay. And the orbit of E and A sub y will now be, it's the same horizontal plane, but over height actually you go, now the height will be determined by this point which will be 0, 0, y. Okay. So it will be the horizontal plane passing through 0, 0, y, but again, the vectors in the unit tangent bundle will be all upward normal vectors. Okay. And I guess in this picture, I'm assuming y is less than 1. And since actually we are assuming this orbit is discrete orbit, actually this corresponds to the case that actually we have this NM orbit inside the G over gamma closed. Because, and then since I'm looking actually also G over M actually, we can show that actually also using the assumption gamma is torsion free. In fact, we just are simply looking at this. So we are looking at this closed N orbit, and then we want to understand the translation of this closed N orbit by AY as y tends to 0. I mean, the reason actually why we're sending y tends to 0 is that if you send actually y tends to infinity, so because of the metric in hyperbolic space, everything actually becomes trivial. So we want to send y tends to 0. I mean, in this picture, if you look at this T1 of H3, of course, everything looks trivial. But of course, the problem is that we have to understand in this quotient space. Okay? But a good example to have in mind is this because our Apollonian group precisely looks like you have some here circles or the hemispheres, and then just the exterior of these hemispheres give you a fundamental domain. So you can have this example in mind. Our gamma has a fundamental domain precisely which are exterior of some of these hemispheres, which could be tangent to each other or disjoint. And then we want to understand the distribution of these unit normal vectors as we push down like to this xy plane. Okay? And then, of course, when you project this to the fundamental domain, things will happen, and then we need to describe what is the distribution of these unit normal vectors as y tends to 0. So this is what's called the equidistribution horosphere. And so this assumption here, so if this is closed, then we can identify this orbit as n quotient by n intersection gamma. And then what is n? So n is simply 1, z, 0, 1. Z is from C. So this is simply the complex plane. So you have a complex plane, and then here you have a discrete subgroup in C. Okay? So this closed orbit can be identified with one of these three. Okay? So it's either R2 or R times R over Z or R times Z over R times Z. So if n intersection gamma is trivial, you have R2, and if it's a rank 1, you have this case, and if it has rank 2, you have this case. Okay? And in the case when gamma is a lattice, actually, it is necessary that actually this quotient space, if you have a closed n orbit, it will always have to be compact. But if gamma is not lattice, actually, then like all of the three cases happens. It can happen actually depending on how gamma looks like. Okay, so now, so what is the distribution of these translations of closed horospheres? I wanted to state the lattice case first, but maybe let me do that. Okay. So I first state the lattice case because the statement for non-lattice case is actually different from the lattice case, so it will be interesting to see how different they are. So lattice case means that suppose delta is equal to 2, or equivalently gamma is a lattice. Then to understand this equidistribution phenomenon, so usually what you do is you take any, say, smooth function with a complex support in the unit tangent bundle or in this double quotient space. In the lattice case, actually, you don't need this quotient as well, but let me state it this way, actually, for comparison. Then the integral precise a n z a y dz. So as y tends to infinity, actually, so this converges to the Haar measure. So space average of this function with respect to Haar measure here. So G from G over gamma, or the double quotient, but times the volume of gamma and intersection gamma. As I said, in the lattice case, the closeness always implies that this quotient should be compact, so the volume makes sense. This is finite, and then divide by volume of gamma of G. And one has error term. Okay. So for lattice case, so for instance, in SL2R case, in the dimension 2 case, I think this was first proved by Peter Sana, and then he gets very sharp error term here. And in the lattice case, actually, this equidistribution is known in great generality. For any semi-simple Lie group, for any lattice, you take horosphere, you can do this. And this can be done so-called by mixing for the geodesic flow. Mixing for the geodesic flow. Plus a thickening argument. And it's due to, say, ask McMullen. So let me explain actually where this main term comes from. Okay. So I give you actually the heuristic proof of this theorem, like just to explain where the main term comes from. So if you look at L2 of G over gamma, and if gamma is a lattice, then it always contains a trivial representation because the constant function is L2 function here. So you get the spectral decomposition, constant function times the orthogonal complement. So maybe C1 also on a complement. And if you have a function here, then you can write this function as psi 1, 1 plus psi perp. Psi perp is simply defined by the difference of these two. Okay? So now if you look at the integral of psi here, n intersection gamma and ay, you simply plug this identity, then what do I get? So this is simply constant, right? And this integral is precisely the space average of psi with respect to Haar measure. Okay? So you get this Haar measure. Because this inner product is just inner product in L2 G modulo gamma with respect to usual Haar measure here. And this 1 gives exactly the volume. So if I put 1 here, then I get exactly the volume of this compact quotient. So I get the volume. And then I need to have the same thing for psi perp. Okay, where did this volume of gamma over G go? I normalize this 1 to be a unit vector. So that makes this volume of G modulo gamma to be 1. So then you have to show that this thing has to be big O over y to the eta. Okay? So I just wanted to explain where we get this main term from the spectral decomposition. Okay? And then our answer for general discrete group, I mean, when delta is between 1 and 2, actually, will look actually similar to this if you are given the right formula for the spectral decomposition. So now let me state the theorem. So now delta is between 1 and 2, and we look at L2 G over gamma. So how does this decompose? So it does not contain 1 because it's an infinite volume. 1 is not L2 function. But by Lax-Phillips theorem, actually, so we get actually smallest representation, which I'll denote by V maybe, and then V perp, where V perp, this is the unique, now infinite dimensional, irreducible representation of G, where the Casimir operator, now the Laplace operator acts on K invariant functions. But there's a Casimir operator which acts on this level of G over gamma. This Casimir operator has eigenvalue precisely here, delta 2 minus delta, where C, the Casimir operator, acts by delta 2 minus delta. But now if you can further decompose V as orthogonal sum, so which you'll write like this. So what is W sub L? So this here decomposition is with respect to the K representation. So as K, which is PS2 representation. Okay. So V is a representation of G. So of course it is therefore representation of a smaller group. So you can again do the decomposition. And then by just, I forgot the name of which term. So it's Peter-Weiss theorem. By Peter-Weiss theorem, you get this orthogonal decomposition here. And then WL is the representation of K of dimension 12 plus 1. So the finite dimensional representations of K, since K is a compact group, every unitary representation is irreducible unitary representation is a finite dimensional representation, and they're all classified. And then here, actually, we get this W sub L. And W sub L has dimension 12 plus 1. So you see already actually how complicated it is actually compared to the lattice case. Lattice case just is one dimension. So here we have infinite dimension. But now, so this is actually 12 plus 1 dimension. But if I look at the M invariant vectors here, then things look better. So if I look at M invariant vectors, then WLM turns out to be 1 dimension. And moreover, it is spanned by real valued function psi of L. So where psi of L is a real valued function, which is not obvious. In C infinity, say G over gamma over L. Maybe, yeah, I'll have 2 more minutes. So, and we prove that if you integrate psi of L and n over gamma, and then nzay. So note that, in fact, even though actually we get close to n orbit, in the non-lattice case, actually, this could be unbounded set. So we always have to worry about the convergence issue. Okay? But we prove actually converges, and it is moreover of this following form. It's some CL times y to the 2 minus delta. And then CL is some non-zero number. And now finally, we can state this theorem. So psi is a smooth function with a complex support on T1 over H3 over gamma. Or equivalently in this double quotient space. And again, we want to understand that this NZ, AY, DZ. Yeah, I'm always assuming that this horosphere is closed, and also gamma, delta is between 1 and 2. Then what do I expect here? So, like using the similar heuristic approach, actually. So, because I have this decomposition, so I can write psi as an infinite sum of psi phi L, and plus psi perp. Yeah, because if psi is M invariant function, so it will pick exactly 1 phi L over here. Okay? So therefore, what we expect is this. So we get this L, the infinite summation, and then this integral, and then now integral with respect to this psi L is exactly looks like this. So that's what we prove. So therefore, here it will be CL, and then psi phi L, and then y to the 2 minus delta, which comes from here, and plus O of y to the 2 minus delta plus eta. Or I can simply also write like this. Okay, so since you have here infinite sum, I have to tell you why this infinite sum converges. But moreover, so here, in fact, this sum absolutely converges, and CL times this psi phi L. This is always bounded above by the second suboverlap norm of actually psi. And since psi is a smooth function with complex supports, this is finite. Okay, so yeah, so this is the effective equidistribution statement for closed horospheres, and maybe one remark actually how it is different. Again, actually, if this psi is K invariant, then this theorem was proved in my paper with Kontorovich. And in that case, actually, if psi is K invariant, and then since phi L are actually non-K invariant functions, so whenever L is not equal to 0, all of this term will disappear. So you get actually one term. Okay? And this trivial K type is exactly what is called this Peterson-Sullivan base eigenfunction corresponding to this Laplace operator. And in our proof with Kontorovich, so we used the very explicit form of this phi naught given by Sullivan to prove all these convergence issues, and then basically to thicken actually this part again. Okay? And when you do this, actually, we had to carry out the same thing for phi over L. And for that, actually, we had to know explicit form of phi over L. And then computing this explicit form of phi over L was, I think, the most difficult part of the proof. And then also, we had to carry out all the computations actually uniformly for all of phi over L. So I think it's interesting also that, it's pretty amazing actually that Sullivan could, or Peterson-Sullivan could have written down the explicit form of the base eigenfunction for Laplace operator. And then we also actually describe all the now actually non-trivial K types of these base eigenfunctions in this work. Okay, so I guess I went over 5 minutes. Thank you.